In terms of Newton's laws, you need to know a few basic definitions. You need to know what weight is. Weight is a gravitational force that's equal to mass times gravitational acceleration. And close to the planet Earth, gravitational acceleration is 9.8 meters per second squared. Anything that I could have given you about balls throwing up in the air and things falling and dropping and being subject to gravitational acceleration on Earth, I could ask you the exact same questions on Jupiter, except I would need to give you the value of G for Jupiter, or I could ask you the exact same questions for the Moon, and I would need to give you the values for G for the Moon. So as long as I'm giving you the gravitational acceleration, we can throw objects up and down in the air as much as we like on any planet, and the same rules are going to hold true. The next one is normal force, which we symbolize with a little F with subscript n. It's a force that is perpendicular to the surface of the object, perpendicular to the surface, and it is exerted onto the object. And then frictional force always opposes the motion and is always parallel to the surface. So we're going to have a perpendicular force and a parallel force, and that obviously links directly into inclined planes. When we're doing frictional force, it has got a frictional force is equal to the coefficient of friction multiplied by the normal force. You can get coefficient of kinetic friction, coefficient of static friction, but we won't ever combine the two at school level. So pretty much if they're going to ask you about the coefficient of friction, it will pertain to the circumstances that are in the particular problem. Don't forget about free body diagrams. So for example, if I had an inclined plane and I had to draw a free body diagram onto this object, I would say that weight, you have to write out the full words. Then there is a frictional force. With a free body diagram, we use a circle to represent the object, and the forces are always arrowed away from that object, and that is a normal force. So that would be a free body diagram. If I had to do a force diagram, and this object is, let's say, on a string, and there's a pulley system or something like that going over there, then I can easily enough just go, okay, well, that's weight. And if I want to, I can put tension up there. I still have to use full words, but I could have, it wouldn't have been wrong to say tension is over there. I mean, you wouldn't in this circumstance, but it wouldn't be entirely wrong. So a force diagram is much more forgiving. The arrows can go towards or away from the object, but they still need to be written out in full. If I have to resolve a force into its components, I'm going to again focus on an inclined plane because those are the trickiest ones. We would resolve this weight into its horizontal parallel component and its perpendicular component. And if I was given an angle of, let's say, 20 degrees over there, the 20 degrees would move there. And I know this force over here, so that's my hypotenuse, this is my adjacent, this is my opposite side. So if I want the parallel component, I would be able to say that that is equal to whatever this weight is. Let's make it 500 newtons for want of a better number. 500 sine of 20 degrees. And when I'm doing the perpendicular component, it would be, let's say, 500 cos of 20 degrees. And the same is true if I, let's say, had a rolling pin that was being pulled along over there. I can easily enough say what is the horizontal component, what is the vertical component. Say somebody had told me that this was 20 degrees and we were pulling with 500 newtons. I would say there's my opposite side, my adjacent side, my hypotenuse, and again I would land up with the opposite side, which is the vertical component, being equal to 500 cos. And I mean, these aren't the same story, but it lands up looking the same. And my horizontal side would have turned out to be, the vertical would have been 500 sine 20, and the horizontal 500 cos 20. You have to know Newton's three laws. Newton's first law is the law of inertia. Inertia is that property where an object resists change, and you need to be able to state these laws. So write them down, make sure that they're part of your summaries. Newton's second law, when a net force remember we can use the equation to help us. So force is equal to mass times acceleration, which means that acceleration is equal to force divided by mass. And therefore, when a net force is applied to an object, it accelerates. That acceleration is going to be directly proportional to the force and inversely proportional to the mass. And in Newton's third law, an action force has an equal but opposite reaction force. They must be acting on different objects. They must act in opposite directions. They must act at the same time. If I look at this little rocket over here, what is the action force? The action force is the gases going down. What is the reaction force? The reaction force of the gases back onto the rocket, and that causes the rocket to shoot on up. We have to be able to apply Newton's second law. The more you practice, the better you get. Let's say we had an example like this. I would also be able to say that this is going to be 0.98 newtons. I lie. It's 9.8 newtons for 1 kilogram. Mass weight is equal to 1 times 9.8. And I've got a tension acting up. Remember, it's the same rope, so there's going to be a tension acting in that direction, and those tensions are going to be equal. Remember, it's always big force minus little force. So let's just think about it. The overwhelming forces here are 9.8 newtons downwards and 6 newtons to the left. These, which one wins? The entire system is going to move that way. Sometimes this force might be, let's say, 16 newtons, in which case the entire system moves the other way. Let's get rid of that. But in this case, it does go down, so let's go. If we're looking at the 1 kilogram block, we can say that force resultant is big minus small. Force resultant is the mass times the acceleration of the system, not gravitational acceleration for force resultant. Big force 9.8 newtons down, small force tension, so tension is going to be equal to 9.8 minus A. Simultaneously, I can say for the 3 kilogram block that force resultant is equal to big minus small. The big force is the tension, the small force is the 6 newtons that's holding it back. Pretend there's no friction here. There might have been friction as well. You would have subtracted that as well. Force resultant is 3 times the acceleration of the system. So T is equal to 3A plus 6. You then equate your two T's. You get 3A plus 6 equals 9.8 minus A. And you solve it out. You can then work out the tension by substituting your acceleration value back in there.